to discuss about PID controllers. PID or proportional integral derivative controller is basically a feedback based control loop mechanism commonly used to manage machines and processes that require continuous control and automatic adjustment. Its typical application is in industrial control systems and other applications where constant control and modulations are necessary without human intervention. So, in PID controllers, there are basically two terms we care about. The first one being set point or SP, which denotes the actual value of the system, and the second one being PV or process variable, which is the actual value of the system. The difference between them is called the error value, which is denoted by ET, which basically help us correct our controller accordingly. Now let us look at the block diagram of the PID controller. The most distinguishing feature of a PID controller is the ability to use the three control terms of proportional, integral and derivative influence on the control output to apply accurate and optimal control. The block diagram shows the principle on how these terms are generated and applied. It shows a PID controller which continuously calculates the error value ET as the difference between SP and PV and applies a correction based on the proportional, integral and derivative terms. So the controller attempts to minimize the error over time by adjusting the control variable, which can be opening of a control valve, adding a new value to the weighted sum, etc. Now let us understand this by using an example. Imagine you have a surface and you have placed a ball on top of it. Now the original position of the ball can be considered as SP or set point, and the value, if the ball is moved, can be considered as PV or process variable. Now imagine due to some disturbances, for example an earthquake, etc., the ball starts to roll in one direction. So how do we bring the ball to the actual position? This can be done by tilting the board in the other direction. This way the ball can change its direction and continues to its original position. Now this way works, but what happens if we tilt the board too suddenly? Due to this, the ball may overshoot and fall off the board. So this is why we need all three terms of the PID controller, the terms being PI and D. So let us look at their importance. The term P is proportional to the current value of the error. For example, if the error is too large, the Kp constant will also be large. This helps us account for the error in our calculation. The next term being I, it is the sum of all the previous errors and it integrates them over time to produce the I term. For example, if there is some residual error left from the previous cases, it can account for those and help us eliminate it. So imagine if all the previous error has been accounted for, the I term will start to diminish and it will not affect our result much. The next term being D or derivative. It is used to estimate the future trends. For example, it measures the rate of change. So if the change is occurring too suddenly, it's gonna account for that. So the main use of D term is to eliminate the problem of overshooting. Now we can tune these variables by various means. Now let us look at the control function. The overall control function is given below, which is ut kp into et plus ki integration of the error function plus kd into derivative of the error term. So this is the standard form of the control function. Uh, the term which we are used to is in the form of Laplace. Here the transfer function in the Laplace domain of PID controller is given, where S is the complex angular frequency. Now let us look at a real life example. In this diagram we can see how the temperature is being controlled. So if the temperature difference is large, we will account for it by using a larger proportional value, and if the rate is slow, then we can decrease the kd value, etc, etc. For example, this can also be used in case of acceleration. So in this example, if we see, if a car is driving uphill, then the engines will be facing more resistance, and the acceleration might not be constant, so we have to adjust it accordingly. Also, let us look at how a PID controller actually looks like. So for example, this is an example where the PID controller is used to control the valves, and the next examples being flow controllers, which manage the flows of oil, gas and steams in pipeline, refining operations and other production processes in oil and gas industry. So another application includes pressure controllers, which help us manage the pressure in distillation columns or separators, etc. And also it can be used to manage the power supply as well, where the amount of power given can be controlled. After seeing all these advantages, there are also a few disadvantages of a PID controller, such as it is not an optimal controller. We have to define the values of three variables, and there is no particular solution. So in large industrial application, PID controllers are not used. For example, other better options are there, so PID controllers may not be used. Also, PID controllers are not well suited for non-linear systems, as they work best for linear. In complex systems, their performance may degrade. But it can still be used for smaller system, as these PID controllers are simple to design and effective in that case. Thank you.